Welcome to Natural Habitat Adventures Daily Dose of Nature. I'm your host, Sunny Vanderstar. Today's topic is more mass extinctions. Discover the age of fishes and how it ended. And it will be presented by our fabulous NatHab Expedition Leader, Eleanor Edye. Eleanor, thank you again for being here today and for bringing us another enlightening topic.
Thank you so much, Sunny. Happy to be here. And it's hard to say that I'm happy to once again talk about mass extinctions, but I do really like looking backwards in time and having a kind of a detailed look at how the world used to be and how it could have looked different than it does now. So as Sunny said, my name's Eleanor. I'm one of the Canadian expedition leaders, and I seem to have fallen into doing a series on the mass extinctions of the world here. So we've previously talked about the Great Oxygenation Crisis. We've also talked about the end Ordovician mass extinctions, and we're here today to talk about the Devonian mass extinctions. So this was a period of time about between 420 to about 360 million years ago, roughly halfway through an age of what we call the Paleozoic, so the old age of life. At the end of the Devonian, as we'll talk about, there wasn't just really one main driver of mass extinction. There was a prolonged period with local and worldwide stressors, along with repeated intense cycles of climate change. This time gave us the result of a massive worldwide decline of biodiversity. So we were looking at a decline of between 70 to 80% of all animal species around the world. If you can believe this, a decline of 96% of all vertebrate species. Just take a time right now to think about what our world would look like if we lost 96% of all vertebrate animals on this planet. So we lost 96% of mammals, 96% of fish, 96% of birds. It would be completely devastating to the world as we know it. And altogether, we had a loss of about 20% of animal families. Now, last time I did a talk on mass extinction, I wanted to give some kind of context for what we were talking about. I'm going to repeat a little bit of that information just briefly for anybody who didn't catch the last one here, and talk about mass extinctions in general and trends in biodiversity. So here we're looking at a graph of biodiversity increases over time, where we're looking at older on the left, more recent on the right. Number of species in the water tracked on the blue line, number of species tracked in brown represent land species. So overall, despite the fact that we're talking through a bunch of mass extinctions, we are looking at across the board a general increase over time in biodiversity and in species richness. In terms of why that might be, there's arguments that perhaps we're not capturing all of the species numbers from the past. That's certainly possible, but also just that as new habitats open up, whether it may be a new ecosystem, a new piece of land, a new piece of water, that allows species to then diversify into those new habitats and make new species. And there may be other species that then specialize on living on that new species, and it kind of trickles down that way. But we're not only getting new species. Obviously, we're here to talk about extinction events. There is what we call a background level of extinction in the fossil record, about one species per million species found on the planet per year. So in any given year, of all the millions of species, we would expect a baseline number that are going to go extinct, along with some number that are going to then be new and newly evolved, giving us a general, equilibrium between extinction and evolution. But in a mass extinction, species go extinct at a rate much higher over a shorter period of geological time. And as we talk about mass extinction, we're usually talking about a rate of about 75% of species loss over 2 million years or less. Now, the Devonian is spread out over a larger period of time with a number of individual events within it, each of which may have qualified as a mass extinction. So we tend to lump them together because they occurred approximately at the same time. As we go through the slides today, we're going to be looking at different taxonomic levels. When we talk about a species, that's a unit of life where they tend to look the same, tend to behave the same, tend to interbreed within each other. But then we can also go up that taxonomic ladder. So the difference between a species and a genus is one level up. A species would be, for example, here like a red fox. A genus would be all of the foxes together. And then a family would be all of the dog species lumped into one family. So when we're talking about species loss and genus loss and family loss, often when the number of species lost may sound really high, but if I tell you that 20% of families are lost, that should tell you that that is an incredible number as well, because to lose 20% of the diversity at a family level is quite high, because then we're talking about taking out, all of the dogs or all of the whales or something like that. Okay. Now, we're here to talk about one of the big 5 mass extinctions. These are, they may not be the only mass extinctions. The better we get at looking into the past, the more evidence we see that there may be more than 5, or we are able to tease them apart to specific events. But we still generally talk about the big 5. The first of the big 5 was the end Ordovician extinctions that we talked about last time we were talking about mass extinctions. And now we're moving on to talk about our next mass extinction, shown here in orange, the late Devonian mass extinction. And one thing I'll point out here is that when you look at these mass extinctions for the other periods of time, you tend to see this abrupt drop like we do at the end Ordovician in that dark green on the left-hand side, or on the light green on the right-hand side, the end Cretaceous, when all the dinosaurs disappeared, boom, abrupt drop, because we're looking at a very short period of time. If you look at that orange part, the Devonian, you can see it just kind of keeps falling off over a very long period of time. So we're going to be looking at the causes and reasons for that. Just to line you up into how far back we're looking, our top arrow here is pointing you towards the Devonian. Next arrow down was the Ordovician. That was what we talked about last time. And then way back billions of years ago, that's Great Oxygenation Crisis. So when we talked about the end Ordovician, we talked about the end of the world that was called the sea without fish. So it was predominantly a sea-based world with very little life on land. Today we are going to be talking about the Devonian, also known as the Age of Fishes. So let's talk about what the Devonian world looked like and what was living in it during this time, prolonged time of crisis. So we'll start by looking at the climate and geography. I'll just bring up the Devonian here. So if we're looking at the temperature of the Devonian, we are looking at temperatures that did fluctuate, and I'll show you some other graphs kind of as we go as well. The overall trend was relatively stable, but if we look much granular, as we will later, we'll see that there's a lot of fluctuations within that Devonian time period. Remember, it's spanning 60 million years. That's a period of time that's really hard for humans to comprehend, never mind the billions of years. Like, humans as a species have only been around for 200,000 years. So here we're talking about a period of time that's many times even just the length of our species life so far. So here it is here, and if you look at the lower curve, that is the level of carbon dioxide within the atmosphere. To give you an idea how much higher it is than today, if you look at that dashed line along the bottom, that gives you all of these numbers are relative to today's level of carbon dioxide. So it starts off incredibly high, but still a little bit lower than it was in the Ordovician, and then just drops like a rock as we go through the Devonian. So like quite an incredible drop in carbon dioxide. Next picture here is what the world looked like. So this was the early Devonian here around 390 million years ago. As you can see, we have two main land masses. So there's Gondwana, which is an agglomeration of what is now Australia and Antarctica and Africa, as well as some other bits that were kind of mostly attached. And then we have another continent called Euramerica, which included, well, as the name would suggest, parts of Europe and a lot of America too, including Greenland. Now, something that I'd like you to notice is that sea levels were pretty high at this time. Remember, we're talking about, at least at the beginning, a period of time where carbon dioxide was high, temperatures were relatively high. All of those coastal seamounts were flooded, giving us a lot of shallow epicontinental seas, so seas that are over those continental shelves. And a lot of that landmass was centered around the equator. So parts of it would certainly have been fairly dry and perhaps even, desert-like, but it was also a lot of that land would have been quite attractive to animals and plants of that time. So good habitats. Nothing. We're not talking about massive ice sheets yet. And so this was a time where we had these land masses towards the equator. It was a time when most of the species that we would recognize as living today don't yet exist. And it's also a time with, because of all of these epicontinental seas, we are talking about huge, extensive reef systems. So the most geographically widespread reef systems in Earth's history, like so much more than anything that we have seen today. So to give you an idea of what a reef system in the Devonian looked like, we can look at something like this. So if you recall back to what we talked about last time during the Ordovician, end Ordovician extinctions, we talked about a widespread, maybe not extermination, but widespread extreme decline in reef species. Sponges likely survived. A lot of the coral species did not. So some of the species that we have here in the Devonian are ones that remained and did not die throughout those last mass extinctions, but many of them are newly evolved species that are now filling the niches that were left open at the end of the Ordovician. So at their peak, we estimate that these reefs during the Devonian covered over 5 million square kilometers, more than 10 times the extent of the reef systems that we see today. So pretty amazing stuff. The species that made up these reefs aren't ones that we would recognize as reef builders today, because most of these species were lost at either at the end of the Devonian or at other times with future mass extinctions that we haven't talked about yet. But we had species of corals like rugose corals and tabulate corals. So the left-hand side there are rugose or horn corals. Tabulate corals were kind of the shelf-making corals. But we also had a lot of sponge reef systems as well. And this on the right-hand side there is an example of a fossilized sponge reef. So a stromatoporoid, if you want the fancy word for it. And just like now, when you have extensive reef systems, those systems are their own ecological habitats. So we see a lot of species diversity within those Devonian reefs as well. So things like brachiopods, we talked about brachiopods before, they're still around. They got knocked back at the end of the Ordovician. They have gone on to rediversify. Crinoids, those sea lilies that you can see on the top right, did not so badly through the end Ordovician extinction. They continued to do well throughout the Devonian. Trilobites got knocked back a little bit, well, a lot at the end of the Ordovician, but they have gone forward and rediversified. And then we start to see a new group called ammonoids. So ammonoids are now extinct spiral-shelled cephalopods, closely related to things like octopus and squid and cuttlefish, and nautiloids that we had before now, but ammonoids are new on the scene. But probably the biggest change that we see from the past to now is that we have gone from the age of, seas with no fish into that age of fishes. So we see a tremendous diversification of fish species at this time, from cartilaginous fishes, so fishes where their internal skeletal structure is primarily composed of cartilage, bony fishes, as well as a group called placoderms, which we'll talk about in a minute here. So this down here is an example of a cartilaginous fish. It's an early shark. I just threw that up there because I think it looks kind of funny. And I like the way it looks. So let's look here at this graph here and at our age of fishes and at our diversity. So here are orange kind of coming across here, our Devonian age of fishes. All of these groupings that we see here are different groups, taxonomic groups of fish. So on the left-hand side, we have our jawless fishes. And as you see, as it extends upwards in time, up towards the present, up at the top here, it goes from being a big group with lots of species down to very few. So today, the jawless fishes are represented just by hagfish and lampreys, which we consider to be pretty primitive fishes. Right? They don't have jaws. That's fairly primitive, as well as a number of other categories. The placoderms, which are the armored fishes, and as you can see, they diversified during the Devonian and then ended at the end of the Devonian. Our cartilaginous fishes, which here include sharks, started to diversify in the Devonian as well, went through a number of radiation events and are still a pretty good amount of our fish population now. Our next group here is a group called the ray-finned fishes. So they got their start in the Devonian as well. Today, the ray-finned fishes represent the vast majority of the fish that you may ever interact with and are actually representing about 85% of all vertebrates currently on planet Earth. So they are a tremendous bit of our current biodiversity, and they got their start back in the Devonian. The lobe-finned fishes are ones that we're going to talk about more because they also diversified within the Devonian, are still existing today in fish like the coelacanth, but we think of the lobe-finned fishes as being most important because they went on to give rise to all of the groups of tetrapods that are living today, like amphibians, reptiles, birds, and mammals. They got their start at the very end of the Devonian. So a lot was going on in terms of biodiversification at this time in the seas. And I want to show you some pictures of the placoderms because I think they are just some of the craziest things. As I mentioned, the placoderms are the armored fishes. So on the right-hand side here, we're looking at, this is an artist's representation here of one of our armored fishes. And then on the left-hand side, we are looking at what is left for the fossil. So they were primarily armored towards the front of their body. And like here we're talking about bony armor that may have been an inch or more thick. And then the back end of this fish, which is where, it had to be able to swim, to move around, was not armored. Probably the most famous of all the armored fishes was this guy here, Dunkleosteus, who was named for a famous paleontologist. So they were some of the largest placoderms. I think some of the most kind of freaky and scary looking. I used to be a museum guide in Winnipeg, Manitoba, and the Winnipeg area was a place that was covered by shallow seas in the Devonian, so we have fossils of animals like this around. And if you've ever had a chance to stand next to one of these guys and really get a frame of reference for how big they were and how utterly terrifying they must have been to come across in the sea, I highly encourage you to do so. So these guys were armored again towards the front of the body. They were suction feeders, so they were jawed, and their jaws were hinged not just on the bottom jaw, but also on the top jaw. So they would open their mouth very quickly, creating suction, and then close their mouth with those armored plates, basically biting their prey in half. And there's evidence through a lot of fossil detritus in old Devonian seabeds that likely these guys just came along, bit their prey in half, didn't even go to get the other half of the prey that had fallen down, and they just go on and take bites of anything else that was around it. So they were quite voracious and quite large as well. The biggest one was up to about 30 feet long, and there's a little human down there for size reference. So I don't think I would be enjoying my time if I had to swim around with one of these placoderms here. Now, I called this an arms race a little bit tongue in cheek, but it really was, right? So we're looking at a time where all sorts of fish are diversifying. We had our ray fin fishes, our lobe fin fishes, our placoderms, our, all of these different fish. How do you, if you are not a placoderm, if you are not a top predator, what is available to you as an option except just being eaten? So this is the time where we start to see evidence of animals leaving the water. And it's kind of nice to think about, well, perhaps they were just doing it to get away from Ductylus osteus. The first, not really tetrapods because they didn't have 4 legs. They had lobed fins. They were able to support their weight at least a little bit out of the water. Were animals like this. This is an animal called Tiktaalik. We call him a proto-tetrapod because they are like one of the beginning of the line of tetrapods. Tiktaalik is actually an Inuktitut word. This animal was found up in northern Canada, and the name means large freshwater fish. You may also see animals like this referred to as fishopods because they are kind of one of those in-between groups between the fish and the tetrapods, not really one or the other. They didn't do well on land. They couldn't walk, but they could support themselves. And they were likely, comfortable in the water as well. I like Tiktaalik for so many reasons. He looks kind of goofy. There were so many, just to pop into internet culture for a second. If you are present on the internet at all and you were there about 3 years ago, you probably saw about 1 million memes that came up with Tiktaalik. Basically, just with the joke being, it's not great up here, Tiktaalik, just go back in the water. But there's another example of what we think this animal may have looked like. So we're again looking at something that's fishy, big head, just like it still has fins, but those fins are able to support its weight out of the water. And this was the grouping that went on to give us the origin of tetrapods. So all of our ancestors, whether it's amphibians, reptiles, mammals, birds, we can all look back towards an animal like Tiktaalik, towards one of those fishopods as one of our, distant ancestors. And this speciation, again, happened pretty quickly. The Devonian is really a time of great innovation. So we have this is just kind of looking at our fish here, our ray fin fish up top that have gone on to keep giving us a lot of ray fin fish. But as we come down towards those lobe fin fish, we start to see a lot of innovation within the structure of those lobed fins, quickly going on to produce weight-bearing structures in animals like Tularpiton, and then eventually the group of living tetrapods like us. We are tetrapods, we have 4 limbs, and we can track our lineage back to these animals. So the Devonian is very, it's very important to us. We can look at it and see how important it is for giving rise to animals like us and all of the animals that we look at today as being important to our daily lives. So here's some other examples of both fish and fishopods at this time. So this was life in the water. How about life on land? So in the water, great time of innovation. On land, now if you recall when I was talking about the Ordovician before, we really didn't talk about the land too much because there wasn't much going on land. Before the Devonian, we had evidence of very small plants like mosses and liverworts. So what we call non-vascularized plants, ones that have to conduct water simply through osmosis through their tissues. And we also had evidence of fungus. So this fossil that this person's working on here is actually a large fungal fossil called Prototaxites. For a lot of years, we weren't sure what this was, and we now know that it is a large fungus that would have been present on land before major plant species arrived on land. So it's anybody's guess what this may have looked like. You'll see artist reconstructions that kind of look like this. That would be pretty amazing to have little moss forests down below you, that are just a few inches tall, and then great big towering columns of fungus. It may have looked like that. This may be a rolled up fungal mat. We're not quite sure, but suffice it to say, pre-Devonian, there was life on land, but not much. And it wasn't very fancy. And it was definitely fungus, definitely moss, definitely nothing else yet. So moving into the Devonian, though, we have so much happening on land as far as the plants go. So the Devonian represents our first significant radiation of life on land. So we go from having just moss at the beginning. I love moss. I hate to say just moss, but let's be honest here. It's pretty small and doesn't do a whole lot for the land. So going from moss-like species to legitimate forests by the end of the Devonian. So we had a diversification of spore-bearing land plants like horsetails, like lycopods, like ferns. Then we also had the evolution of vascular plants. So the first vascular tissues, water and other conducting tissues within plants. We had the evolution of leaves and roots. We had the evolution of seeds. And we also had the evolution of secondary growth when a plant can grow both outwards as well as upwards, giving us the first wood. All of that gave us the first trees and the first forests. So pretty crazy, like massive diversification of life on land here. And it's all happening within this period. So just to give you some kind of ideas for what we're looking at here, some of the earliest vascular land plants maybe didn't look that impressive to you. This is called Cooksonia. It's an extinct group of primitive land plants. It was a spore-bearing plant, so it didn't have seeds yet, but it did have the first start of vascular tissues, so it was kind of what we call an evolutionary jump away from the mosses here. We had large species of lycopod. So lycopods we still have around today. They're things like ground pines or ground cedar, ground spruce. They're little plants about yay high that produce a spore-bearing strobolus at the tip. And they're kind of fun because those spores are very apt to catch on fire. So if you go walking through a patch of this when you're camping, you can get sparks happening on your feet if you sit too close to the campfire at night. But these guys were actually large plants back in the Devonian, so we still have them around as small plants, very limited number of species. Here we're talking about forests of lycopods in the Devonian. First wood. So this is the first woody plant that we know of going back about 400 million years. So you can see the cross section of that plant with the outward growth happening here is as far back as we can track that invention of wood. But by midway through the Devonian, we had forests. And these forests continued to develop, and we had more species coming in, but forests were present by midway through the Devonian. So again, lycophytes, horsetails, ferns, what we call proto-gymnosperms, so plants that came before things like spruce and pine and our other coniferous type of trees. So these plants had leaves, these plants had roots, and these plants had secondary growth, so growth outwards. Again, today we still have some limited numbers of these groups left. So if you look on your left-hand side, that's a current picture of a horsetail. You might also know it as a scouring rush. These types of groups produced trees back in the Devonian. And here is an example of what we call our first true tree, because it was from a progymnosperm with fern-like leaves. This is Archaeopteris. You might know the word Archaeopteryx. It's one of the fossils that's well known because it's an intermediate form between birds and dinosaurs. It's a feathered dinosaur. But Archaeopteris is one of our first known species of trees. And again, going back to now the late Devonian here, we think that these trees, once they did evolve, spread out quite quickly across the land. So I'll just leave you with a picture here of what a Devonian era forest may have looked like. But this period of time and the rapid appearance of all of these plant groups and growth forms, we call the Devonian explosion or the Devonian terrestrial revolution, because it truly was a new way of existing that had not existed before. We've gone from our little mosses and liverworts and fungus only to legitimate forests. Those forests represented, actual ecosystems that had arthropods in them. Trees had interactions with fungus, same as they do today, to increase their absorption. We would recognize, if not the exact ecosystems that we're looking at, we'd recognize the parts of these ecosystems. Yeah, there's trees, there's bug-like things, there's fungus things that all come together to give us these ecosystems. So we had early spiders, we had early millipedes and centipedes, and we had, as we've said before, vertebrates just starting to take their first shuffling steps onto land as well, giving us those first terrestrial ecosystems, like here. So wow, doesn't this place look great? Isn't life wonderful? What a great time to be alive. I sure hope nothing happens to the world of the Devonian. Ah, if only we could have just kept going as fish, if only we could have still seen those forests of lycopods and horsetails and those early gymnosperms like we had then. But sadly, this was not to be, because as this world was developing, it was really already laying the seeds of its own destruction. So we've already kind of alluded to the fact that the Devonian extinction wasn't just a single extinction event. It was multiple events done over a prolonged period of time. So here they're showing our arrows. These are two separate events that we often refer to as we're talking about our Devonian extinctions. But if you look around this time, you'll see that extinction rates were never especially very low in the Devonian. So this appears to be multiple mass extinctions. We recognize those two main events, which I'll give you the names of right away. They're generally agreed upon, but there may be as many as 8 to 10 extinction events. This was also a time when not only were we having extinctions, but we were seeing towards the end especially just less speciation too. We'll talk about why that was. But remember here, we're talking about a decline of up to about 80% of our animal species, 96% of our vertebrate species, and 20% of our animal families. So the first main event that kind of came and hit was an event called the Kellwasser event, happened about 372 million years ago. This event affected mostly marine species. At this time, we lost about half of all marine genera. So we're talking here brachiopods, you know, reef-building species, fish, all the marine stuff. Our second extinction event was one called the Hagenberg event. This happened about 359 million years ago, and the end of the Hagenberg event marks the end of the Devonian and the start of what's called the next period, which is the Carboniferous period. This event, the Hagenberg event, was seen over all ecosystems, so not just marine, but now we're talking about the terrestrial ecosystems as well. So as I mentioned, some consider this to be many distinct events spread out over around 25 million years. Remember, I talked about a mass extinction being over about 2 million years, but here we're seeing like event after event, maybe after event after event after event. There's still a lot of things that we don't know about the Devonian extinctions. Believe it or not, there's not a lot of research dollars and time and effort that goes into looking at this. So there's still things that we are learning. So about 70 to 80% of species were estimated lost at this time. But what I think we can really take home from this is that it was an extended time of crisis. So we are looking at, as we'll pull up in a second here, not just one stress, but multiple stresses from multiple sources. There are some things that we know were stressors and some things that we think were stressors. So we have what are called abiotic stressors, so things that happen without the impact of life, so things like volcanoes, we know erupted at the end of the Devonian, and they erupted extensively. There's evidence for meteorite impacts at that time as well. We also see evidence of sea level change quite rapidly over multiple times. We also can look at biotic stressors, though. So one thing life is really good at is causing problems for other life. And plants were really good at causing problems for other life forms that were on the planet at this time. We're going to start with the evidence and what happened for the land plants as stressors. And I've been a little bit dramatic here, and I'm calling them plants of death. But that is really what those plants were for all the other organisms that were living at this time. So remember that before the Devonian, we did not have land plants beyond mosses. So we didn't have any reserves of wood. We didn't have plants growing over every surface of the earth. What plants are good at is a few things, but one of those things is taking in carbon dioxide from the atmosphere, locking it up in their plant tissues, and then releasing oxygen as part of photosynthesis. And through this colonization of plants around the world, we actually saw a drop in global carbon dioxide levels to the point where global cooling happened, giving us possibly some ice formation towards the poles, therefore giving us changes in sea level. So as water starts to be locked up in ice, sea level will drop, exposing all of those epicontinental seas. That's something that we talked about when we talked about the Ordovician end extinctions, is that massive glaciation that happened towards the end of the Ordovician, just killing off all of our sea-dwelling species. Well, we see this happen multiple times as plants innovated and then pushed into new habitats. The other thing plants are good at, once they evolve roots and once they develop those fungal symbioses to allow them to absorb more, is they actually cause weathering of rocks. So weathering is not the same as the physical breakdown of rocks. We're talking here about the chemical breakdown of rocks. So they do things like secrete a little bit of acid, they break down rocks and release nutrients so that they can absorb them for their own needs. This is how, this as well as like dropping leaves and things like that, is how soils are built. Before this time, soils did not exist. All of these nutrients were locked up in those rocks. Now that we have soils and we have, rain, now we have runoff, meaning that those nutrients are going to be washed out of the soils towards the coastal regions, allowing algae in the oceans to absorb and use those nutrients and cause blooms, so grow into large algal blooms. It's pretty crazy to think about how much plants change the world. Now, I think that I'll just take an aside for a second here. As we're going through and talking about mass extinctions, you may have noticed a little trend, is that often as we see evolution of a new type of life, like when we were talking about the Great Oxygenation Crisis, where we switched our world from being, a reducing atmosphere to an oxidizing atmosphere, basically killing everything around it. Life is really good at massive modifications to the atmosphere, the earth, the waters, and trees are no exception to that. So here we're looking at, if you look down at the bottom here, the Devonian is shown in orange. So this is a period that we're looking at here. If you look up towards the top, we see our atmospheric oxygen levels start pretty low and then do a really fast jump and then pulsing continually upwards as we see more evolution happen. So we go from land plants to vascular plants to trees to seed producing trees. And each of these innovations allows plants to colonize a little bit more of the land surface, thereby giving us more oxygen in the atmosphere. And this horizontal red line here is at 15% oxygen. This is something I've talked about in a previous webinar, actually, is this marks the point at which you can have and do get fire on Earth. So once we started having these vascular plants on Earth producing oxygen, now we have ecosystems that are not just driven by, temperature, water regimes, what kind of soils there are. We now have fire creeping in to control what kind of ecosystems we have as well. The converse to this is looking at the atmospheric carbon dioxide. Here is the blue line, starting off fairly high, so much higher than we see today. We're around 400 parts per million now. We started off close to 3,000 parts per million back in the Ordovician, and then as those plants take that up, atmospheric carbon dioxide drops like a rock, goes through a few little pulses. These pulses likely represent incidents of volcanism. So as those volcanoes erupt, more carbon dioxide is released. And all of this changes the world. So we're moving from a world that was a greenhouse towards a world that is an ice house, driven by ice sheets and lowered sea levels. If you look over on the left-hand side of this image, this is the Devonian. The middle kind of blue thing that looks like a squiggly line there is the changes in sea levels over time. And you can see that it is just all over the place, right? The plants were just messing everything up. They take carbon dioxide in, things cool, ice forms, water level drops. Things start to equilibrate again, sea level comes up. Oh, plants do something new, sea level drops again. So we have all of this stress through the Devonian in terms of what the sea levels were doing. And then this right-hand kind of orangey graph here on the left-hand side there is showing us your sea surface temperature. So how warm those sea surface temperatures were also controls things like how well your reefs could grow. When it's really cold, your reefs can't grow. They do require warmer temperatures than that. So we had these pulses of like extreme stress over the world, and then it relaxed, and then another pulse of stress, and then it relaxed. And something that we're really aware of from today is that when we see these periods of fast, hard stress, when organisms don't have time to evolve or change behaviors, this is when we see like prolonged pressure on these ecosystems, and we see a lot of loss of species richness. Okay, so not only were they cooling things off, they also directly killed the oceans, those trees. So as they were, as they were releasing those nutrients from the rocks, those nutrients ran down into the ocean, causing algae to like suck them up and create blooms. So this is a process called eutrophication, when we have a lot of nutrients entering a water source. And this then, what happens is the first organisms that are able to use those nutrients are generally a group called the blue-green algae. So blue-green algae are important. They produce a lot of our oxygen. They're really good at finding areas with lots of nutrients. They eat them all up. They make a lot more algae. And then they die, and they die in such numbers that the decomposition of that algae takes up all of the oxygen in the system, causing any animal or other plant in that area to die. This is called marine anoxia, and we have lots of evidence for this. And you might even be sitting next to a source of evidence for this right now, because if you get your natural gas from a shale deposits, this was caused, these shale deposits are where the natural gas, the carbon from these algae died, sank to the bottom of the seafloor, were covered up by sediments and locked in place, and now we have tapped them and fracked them and are using that stored energy to do things like warm our houses right now. So we have evidence throughout like North America and throughout the world of these mass dying events that were caused by the evolution of trees and roots and soils. Pretty crazy to think how it all connects up. Again, we see analogies for how things work today. We have a lot of hypoxic areas in today's oceans, in areas where we're not doing a good job at controlling things like industrial runoff or agricultural runoff, and we have a lot of nutrients going into the water. All of these red areas here are what are called marine hypoxic zones. So areas where, again, we've flooded the areas with nutrients. Algae have not swarmed in. They show up there, they eat the stuff, then they die, causing all of the oxygen to be used up in that decomposition process. And then we end up with these dead zones where nothing can live because there's no oxygen in those areas. Okay, so plants are killing everything off. There's stress number one. So they're taking up all the carbon dioxide, they're lowering the temperatures, they are actively killing the oceans. Another thing that we see, kind of coming back to the plants, is that we saw those sea level changes coming up and down and up and down and up and down. Well, because we had a lot of our diversification happening in the ocean, every time those sea levels changed, you would have ocean basins that were connected, then not connected, then connected again, then not connected. And when we have an area that connects that used to not be connected, what we tend to see happen then is invasive species moving into the new habitat. So whatever species is better suited and more able to survive tends to be then the one that will survive and thrive. Say you've got 3 species of brachiopod in the area, and they're each living in their own little basin, and they're all like happy and on their own. But if sea level floods, and then all of those ocean basins are connected, those brachiopods are then able to spread and send their young off to these new basins. And it turns out that one of those species of brachiopod just grows faster than the other ones. Well, it's going to end up displacing those other 2 species because now it's invading these other areas. So part of what we saw at this time was not necessarily like an increase in extinction at all times. It was also a lack of speciation, because as these invasive species were moving around the globe, it hindered new species from evolving in these areas that were now connected up. So again, a lot of analogies here to our current situation where we see rapid changes and rapid spread of invasive species. Humans are really good at spreading new species around. So those were some of the biotic factors. Were abiotic factors part of this as well? Yeah, I mean, almost for sure. We have direct evidence of asteroid impact at this time. So this crater ring that you can see here in the image is called the Silden Ring. It's in Sweden. It's an impact site from the end of the Devonian. Could it have caused some of the extinctions? Probably, sure. But it wasn't like a one-time killed everything kind of deal like we've seen with some other meteorite impacts. It was likely one of many stressors at this time. Was there volcanism towards the end of the Devonian? Yeah, we definitely had volcanic activity. There was definitely carbon dioxide being emitted into the atmosphere. We definitely saw like rapid changes in climate as a result of this up and down of the carbon dioxide levels. Would it have directly impacted some species? Absolutely. Was it enough to kill everything off? Probably not. So all of these factors likely combined to cause this like prolonged stress and die-off of all of the species that we're talking about here. And what the outcome was? Well, it was not a great outcome. Lots of species were lost. One of the biggest changes we saw was a fundamental collapse of the reef system. Like all of those reefs that were such an important part of the ecosystems throughout the Devonian pretty well completely collapsed, and we have never seen recovery to the levels that we had back in the Devonian. Our sponge-like coral builders, our stromatoporoids, went extinct. Ammonoids nearly died out, but not quite at this time. We lost them later on. A number of trilobite species died out as well. We haven't lost all trilobites at this time, but we lost a lot. But those reefs and the systems that they supported were probably one of the most important part of this extinction process. You can still see evidence of these fossil reefs as fossil reefs found on land today. One of the more intact sites here, this is in Western Australia in the Kimberley region, where you have these limestone reefs that were formed during the Devonian, around that 400 million year ago mark, before that mass dying event happened. And that curving long stretch of what was once a coastal reef is now found along the western shore of Australia as a rock deposit on land. And again, just to kind of bring it home, what a loss that was. Take a look again at where our continents were, how much space there was for those reef systems to develop across all of those epicontinental seas in those tropical and equatorial areas. Compare it to today when our reefs are really marked by dots as opposed to massive swaths of the globe where we would have seen reefs. So we've simply never seen recovery to the level that we had back in the Devonian. One group that did not make it out of the Devonian were the placoderms, and you might choose to be happy about that because those armored fish were kind of scary. But none of them made it out. None of their descendants survived beyond the end of the Devonian. We lost a lot of our benthic organisms. We lost a lot of our early tetrapods, and we lost a lot of the diversity of our early tetrapods as well. So these days, as we talk about tetrapods, so you and me and my pet bird and my pet dog and all of us with 4 limbs, whether it's wings or legs or arms and legs, we all have a pretty set body type that has been modified for things like flight or running fast. And the base level is 5 digits. We have 5 fingers, 5 toes, And if you don't have that number, it's because it's been modified from that base 5. Well, there was no guarantee of that. Back in the late Devonian, all of those early tetrapods were experimenting with how many fingers and toes were required. So the most common number was actually 7 fingers and 7 toes, but it varied between 3 and 8, or sometimes even more. The reason that you and I have 5 fingers and 5 toes is because the only tetrapods that survived the end of the Devonian had 5 fingers and 5 toes, so 5 digits on each limb. So when we look at our own hands, we can see a direct link back to this period of time. What followed this time was the Carboniferous period, a time where we had a lot of still plant growth on land. A lot of our carbon that was laid down in coal deposits was made in the Carboniferous. But the Carboniferous is known as the age of amphibians. So we did have tetrapods that survived. We did go on to then evolve amphibians, as well as insects and dragonflies and all sorts of, diversity happened again. But this was at a time through the Carboniferous that was also the late Paleozoic ice age. So we went into an ice house and we stayed in that ice house for a very long period of time. As we move forward, the next mass extinction, if we end up getting there, is going to be the end Permian mass extinction, which I hope you'll come by and see me for that, because it was the big one, the one that almost removed life on Earth. But here I see I've gone right up until the hour, but I want to make sure that those who have questions get them answered. So I'm going to hand things over to Sunny here for questions.
Thank you, Eleanor. That was absolutely fascinating. You do such a good job of delivering some pretty complex information in such a simple, digestible way. So thank you again. We do have a few questions, but I want to remind everybody that they can submit questions via the questions field in the control panel. So the first one is, were there any insects present, or when did they start? When did they show up on the scene?
Yeah, true insects were not present yet at this point. We had early arthropods, things like protospiders and those millipedes and centipede-like organisms that I was showing. But it was around 300 million years ago, thereabouts, that we had what we now call our true insects, so the 2 sets of wings and the 6 legs and so on.
Okay. And you might have touched on this, but can you review or clarify if we have an idea how populated the Earth was during this time, like how much biomass, less or more than now?
Oh, that's an interesting question, and I don't know the answer regarding biomass. Um, like these days, a lot of our biomass is organisms that we don't think about too much, right? It's algae in the oceans, and it's certainly we think about forests, but there's a lot of biomass within the insect world as well. If you made me guess, I would guess that we have more biomass today simply because we've had time for more things to evolve, more nutrients to be liberated from the bedrock to then go on and feed other organisms. But what we do know about that early life, especially on land, is that we had those ecosystems, but they weren't being fully exploited yet, right? So we had trees and we had forests, but we didn't have big herbivores. We didn't have a lot of other life on land besides those early arthropods and our early fishopods that kind of flopped around and just were making those first few shuffling steps on land. So just by virtue of that, my strong guess would be that we have more biomass today, but there was a lot back in the Devonian too, especially as we think about those reef systems, that we don't see anything like that today.
Mm. And I think we have time for one more question. Again, this might be a review, but what caused the biggest mass extinction at the end of the Devonian that impacted all ecosystems?
Oh yeah, so towards the end of the Devonian, things that we saw throughout that like second event, we had those pulses that I was talking about, and pretty well all of the things that were happening kind of happened throughout the whole end. So things that happened just at the end that affected both the land and the water, we had so we had seed plants evolve, thereby we were able to then go into new areas again, releasing more nutrients, causing more more algal blooms, more dead zones. We also had definitely volcanism at that time, and also the asteroid impact was towards the end of the Devonian too. So we call it a distinct event because you can see it in the geological record. If you dig down and look at those rocks, it's a big black line because of basically all of the dead things that got buried and turned into natural gas and in carbon deposits into those rocks. But it was likely those multiple causes that combined to cause that mass die off at the end there.
Hmm. Well, thank you
Yeah.
again. I'm going to turn it back to you for closing comments.
Well, thanks, Sunny, and thanks everybody for coming by today. Whew, mass extinctions are always a hard one to talk about, but they're also really interesting to think about the larger context of life and what's brought us to where we are today. And as we're getting kind of closer to our timings, we can really start to see pieces that connect up to our lives today. So I hope that you found things from this that you can see analogies to, or that you can see how they affect our lives now, and lessons that we can learn from this time. Um, I'm really enjoying talking about mass extinctions, so thanks to everybody who shows up for this as well.
Well, we are all delighted by this topic. There's so many comments that I will share with you later from our viewers, just reflecting on how fascinating it is, and again, what a great job you do of delivering it. So keep it coming. But I'm glad to know there's just one more, right? How many
One more
more?
big one. Three more, but one more big one.
I want to thank everybody who tuned in. And again, thank you for submitting such great questions. Please join us again tomorrow for our next Daily Dose of Nature. You can check out this week's lineup, including registration links, on our website at nathab.com/webinars. We did record today's presentation, and we will have the replay available on our website soon. With that, I'll conclude the webinar. Have a wonderful day, everybody.